All right. So we're going to backtrack now and go into Chapter 8, and I'm just going to cover the first couple sections of Chapter 8. Um, Chapter 8 is all about differential equations, and these things come up a lot in the real world. So if you're planning on going into engineering or physics or, something along those lines, then you'll be taking you'll take at least one differential equations class. Like I would imagine most of you in this class right now are probably going to take Math 80 here, which actually you could take, I believe you can take that right after you're finished with this class even. I could be wrong about that. But anyway, yeah, so we're not going to talk in a ton of depth about differential equations, but I did want to briefly introduce you to the concept because we're supposed to cover it in Calc 2 again very briefly. So we'll do 8.1, 8.2, and then that'll be it for the course. So well, let's get into it. A differential equation, you've seen these things probably before, but just to remind you, a differential equation is an equation involving one or more derivatives of an unknown function. The order of a differential equation is the order of the highest derivative that it contains. So, for example, all of these equations are differential equations. This is differential equation has order 1, so we would call it a first order differential equation. This differential equation has order 2, so it's a second order. This is a third order differential equation. And this is another second order differential equation. It's just we're using y prime instead of dy dx. Okay. Like any equation, a solution is going to be anything that satisfies the original equation. So in other words, here, a solution to this differential equation would be some function y, so that when you plug in y here, and when you plug in its derivative there, you get a true statement, right? So let's verify that this equation, c1 e to the negative 2x plus c2 e to the 3x, is a solution to this differential equation, y double prime minus y prime minus 6y equals 0. And this will be true for any constant c1 and c2. So let's verify that. So our differential equation is y double prime minus y prime minus 6y equals 0. And our proposed solution is c1 e to the negative 2x plus c2 e to the 3x. So let's verify that that is in fact a solution. So let's call this thing y. Let's say this equals y. In order to verify that this is a solution, we need to calculate y prime, and we need to calculate y double prime, and then we need to plug in those values. So let's do that. Y prime is going to be c1 e to the negative 2x times negative 2. So I'm just going to call that negative 2 c1 e to the negative 2x. And then similarly, the derivative here is going to be c2 e to the 3x times 3. So I'm just going to call that plus 3c2 e to the 3x. So there's y prime. And then y double prime is going to be, oh goodness, it would be negative 2c1 e to the negative 2x times negative 2. So that's just going to be 4 c1 e to the negative 2x. And here we're going to get what? 9 c2 e to the 3x. And now to verify that this is a solution to the equation, we would plug these things in, right? So we plug in y double prime minus y prime minus 6y and we want to verify that that equals 0. So let's simplify. So I'm going to have a 4c1 e to the negative 2x plus a 2c1 e to the negative 2x. Okay? And then minus a 6c1 e to the negative 2x. So those will all cancel. Here I'll have a 9c2 e to the 3x minus a 3c2 e to the 3x. So that makes 6c2 e to the 3x. And then minus 6c2 e to the 3x. So those all cancel, right? And so sure enough, that's a solution. Okay? So the trick is, if you're starting with something like this, how do you go about finding this solution in the first place? And that's a topic that you'll get into in differential equations when you take differential equations. We're not going to deal with second order differential equations like this one in this class. We'll just do first order differential equations, and in fact we're going to do a type of differential equation that's called separable. Because in order to solve first order separable differential equations, all you need to know how to do is integrate. So we're well equipped to be able to handle those kinds of situations. Okay, this sort of equation right here, this sort of solution is called a general solution. Okay, so the family of solutions in example 1 is called a general solution. And it's a family of solutions because you could replace C1 and C2 with any real number, and it would still be this would still be a solution, right? As a rule of thumb, a differential equation of order n is going to have n constants in its general solution. So just like we saw here, we had a second order differential equation, and we had 2 constants in the general solution. So if you had a fifth order differential equation, you'd expect to have 5 constants in your general solution. In order to solve for these constants, we need to have some more information about the function that serves as a solution. So in particular, since we're going to look at some first order differential equations in this class, we just need to have some more, we just need to know the value of y at an arbitrary x value. And we usually denote that by saying y of x naught, that's our arbitrary x value, equals y naught, that's the resulting y value. Okay? So this thing right here is called an initial condition. And the problem of solving a first order differential equation subject to an initial condition is called a first order initial value problem. Okay. So for example, so number 2 here says, verify that y equals e to the 2x plus c e to the x is a solution to dy dx minus y equals e to the 2x. Then use that solution to solve this initial value problem. So dy dx minus y equals e to the 2x, y of 0 equals 3. So let's do that. So first we have to verify that this is a solution in the first place. Okay, so the initial value problem we have is this: dy dx minus y equals e to the 2x, y of 0 equals 3. And the proposed solution is the proposed general solution is y equals e to the 2x plus c e to the x. So first of all, let's verify that this thing works to solve this equation, or as a solution for this equation. So I need to figure out dy dx first of all. I know that if y is e to the 2x plus c e to the x, then dy dx is going to be 2e to the 2x plus c e to the x. So then plugging this and this into here, we get dy dx minus y equals e to the 2x. And so we want to verify if this is a true statement. Well, 2e to the 2x minus e to the 2x will sure enough give us e to the 2x. Ce to the x minus ce to the x will cancel. And so we just get the identity e to the 2x equals to e to the 2x, which is of course true. Right? So this is a general solution to this differential equation. Now let's solve the initial value problem. Okay? So we know that y equals e to the 2x plus ce to the x. We also know that y of 0 equals 3. So when I plug in 0, I should get 3. Okay? Well, e to the 0 is 1. E to the 0 is 1. So this is 1 plus c. And that means that c has to equal 2. So the solution to the initial value problem is going to be y equals e to the 2x plus 2e to the x. Okay. So that's that. Let's do another example. So number 3 here says find a solution. So they're not giving us a solution this time. They're saying find a solution to y double prime plus 6x equals y. And then we have a couple of initial conditions, which we'll need because we're going to have two constants to solve for, because this is a second order differential equation. I know I just said a second ago we wouldn't solve any of these. This is a fairly easy one that we should be able to figure out. So y double prime plus 6x equals 0. And then our initial conditions, y of 0 equals 1, y prime of 0 equals 2. Okay. So looking at this differential equation, we need to solve for y such that y double prime plus 6x equals 0. So we need to find some function y whose second derivative is equal to, it must be equal to negative 6x, right? Because that way, negative 6x plus 6x will equal 0. Another way to see that is you could just subtract 6x to the other side of the equation, and you would see that y double prime has to equal negative 6x. So we should be thinking to ourselves, we need to find a function whose second derivative is negative 6x. In other words, we need the first derivative, or sorry, we need the derivative of the derivative to be negative 6x. So maybe we can figure out first what the derivative is, what y prime is. If y double prime has to be negative 6x, then y prime must be, it must be negative 3x squared, right? Because that way, when you take the derivative to get y double prime, you get a negative 6x. Now, the only thing is that when you differentiate, you always lose a constant. Well, not always, but potentially you've lost a constant. And so that's a possibility, right? So there's our first constant value that we have to worry about. Okay, but now let's see if we can find, all right, so if y prime is this thing, then what's y? Well, I think y would be, here we'd have to have a negative x cubed. Here we'd have a c1x. And then, again, getting from here to here, it's possible that we dropped a second constant, right? So now you can check your work by going backwards. If I differentiate here, I'm going to get negative 3x squared plus c1. And then if I differentiate again, I'm going to get negative 6x, right? Which is exactly what I want. So this must be the general solution. The only thing I need to do is solve for the values of C1 and C2, and that's where these initial conditions are going to come into play. So we're told that y of 0 equals 1. If I plug in 0 here, well, actually, I could have solved for C2, so that's not terrible. I was going to say we're better off solving for C1 first, which actually means that we're better doing this step first. But in this case, I guess it doesn't really matter. I'm still going to do it the way that I intended, though, and I'm going to plug in 0 to y prime first, because that'll give me C1. So I can say, well, since y prime of 0 equals 2, that means that negative 3 times 0 squared plus C1 has to equal 2, which means that C1 equals 2. Which means that y is really negative x cubed plus 2x plus C2. Now to solve for C2, I use this first one, right? Y of 0 equals 1. So y of 0 equals negative 0 cubed plus 2 times 0 plus C2, and that has to equal 1. Which implies, of course, that C2 equals 1. Putting it all together then, y equals negative x cubed plus C1x, so that's 2x, plus C2, so that's 1. And there's the solution to our initial value problem. So, so these are differential equations. They get much, much worse than this, which is why there's an entire class devoted to them. In fact, as I've mentioned before, there are several classes that you could take. I only ever took one class in differential equations, so I'm far from being an expert. But there are people whose specialty is differential equations. Man, they just solve differential equations all day, and I think they're kind of fun. And you learn a lot of really interesting techniques in the differential equations class that we offer here on campus. So, so I'd strongly encourage you to take it if you weren't planning on doing so already. But just to give you a little more information, and then this will be a short lecture. But differential equations are useful in all sorts of real-world stuff: population growth, the spread of disease, Newton's law of cooling. They're used a lot in electricity. Pretty much if you're doing any kind of physics, right, the thing about physics is that you can oftentimes boil down a whole bunch of different theories into a single equation, and more often than not, those equations are differential equations. So, I mean, they're just hugely important. Like, they just come up all over the place. Anyway, if you want some specifics of these things, take a look at your textbook. And I think that's all I have to say. So we'll come back in 8.2 and talk a little more specifically about solving some first-order differential equations that are separable.